Okay, all right, everyone. So shall we start our session of ideas? All right, please turn on your video of for the speakers of today. All right, thank you very much. And I'm Hiroki Tanikawa from Nagoya University, and also I want to introduce Professor Naho Yamashita for our co-organizer. And today, first of all, welcome to the ISIE Day. This is a worldwide event, or virtual worldwide event. And also we try to joint project, going to be a joint project of the S18 research project, which is our national government, especially the Ministry of Environment funded the project, which is the thinking about for the adaptation of climate change issues. Especially in our group, we are focusing on sustainable urban built environment and climate change adaptation and mitigation. So and in our project, we have the young researchers and in our group. So we are asking to the young researchers to present their research. So okay, I hand over to Naho-san for more introduction. Naho-san, please.
Thank you. Good afternoon, everyone. I'm Naho Yamashita from Nagoya University. Thank you very much for coming to this Japan Tokyo sessions. So this session is on S18 research project, sustainable urban built environment and climate change adaptation and mitigations. So before starting the session, I have some announcements to all of the participants here. So we have a very tight schedule today, so 10 minutes for each presenter. So we will not have a Q&A session for after each presentation, but you can have a questions you can write a question in the chat box at any time, or we can have a time for discussion in the end of these sessions. So we really appreciate for your cooperation to proceed this session smoothly. So I will start the first part, the introduction of the whole research project now. So the official name of this project is Comprehensive Research on Projection of Climate Change Impacts on Evaluation and Adaptations of Adaptations. So this is a 5-year project which aims to create a new scientific information on climate change impact and adaptation measures to support Climate Change Adaptation Act, which was established in 2018. This is actually a very huge project. There are 5 themes and 90 sub-themes under those 5 themes, and more than 25 research institutes with over more than 200 researchers are involved in this project. Just quickly introduce each themes. The theme 1 is like kind of comprehensive management of the whole research project. So they are working for an integrated framework of the climate change adaptation and mitigation in each field. And under that theme 1, we have individual topics from theme 2 to theme 4. For example, theme 2 is especially focusing on the climate change impact on the agriculture, forest, and fisheries. And theme 3 are more like water-related management and water disasters caused by climate change. And theme 4 is human health and human activities and our life in the daily urban built environment. And theme 5 is like wrap up sessions of the project. So they have an economic perspective to how to deal with this climate change impacts. So those 5 themes, each other, they are going back and forth each other during the 5 years period of the research project. And all of the presenters today are from theme 4, which has a title of Projection of Climate Change Impacts on Quality of Life of People and their associated infrastructure and local industry and evaluation of adaptation options. And under this theme 4, there are 4 sub-themes, and we are from sub-theme 4.2, impact projection and evaluation of climate change adaptation measures for sustainable urban built environment. So we have a research group from Nagoya University and the University of Tokyo. And this picture is like the whole vision of our sub-themes topic. So on the top, we have external pressure can be occurred by climate change. And the impacts by climate change, like increase of precipitations or extreme weathers or summer heat waves in the urban environment, have the enormous impact to our life, our daily life, through the impact to the urban built environment, like the existing buildings and infrastructures. And because those the buildings and infrastructures are composed of a lot of construction materials and also consumes a lot of energy for their operations. So there is an indirect impact to those urban metabolism things. So our aim is to evaluate the impact of the climate change on such urban structures like buildings and infrastructures and its interrelated resource and energy flow. And also we would like to propose some adaptive or mitigative strategies toward more resilient urban systems in consideration of long-term CO2 emissions or technological development or human activities. When it comes to more like concrete idea, it can be shown like these pictures. So the same as the previous picture, it's like on the top, we have an impact of climate change, and it has a damage to the urban environment through some extreme weathers or disasters like flooding, landslide, typhoon, and so on. Then those damages have an impact to the urban environment through the changes of inflow and outflow, and the material stock itself. We call it urban metabolism. So they have an great impact to those urban metabolism management. When we think about how to prepare for coming damage by climate change, we can think of many advanced adaptations measures, such as relocation of the infrastructure, like existing infrastructures, or reinforcement of the embankment, for example, or ports, or reconstruction of the buildings with a higher ground level to avoid the risk of flooding in future. But those adaptive measures can be tricky sometimes because it induces more like carbon emissions or the other environmental burden in the background of those production or constructions or demolitions. So under those ideas, we have a specific individual research topics, many topics. I cannot pick up everything here, but yeah, in the 5 years project, we have many targets underneath those our aims. And here I picked up some representative ideas of our research. And on the left side, I highlighted 4 of them. And I think those 4 topics are presented today after the presenters, after my presentations. So, but firstly, I will quickly introduce the one topic from here, development of material stock flow database, which can be a fundamental research of this S18 project. So this is kind of continuous work from the past to the current. Firstly, it was published in 2015. You can access to the original paper from this QR code, and we continuously collecting the database for the buildings and infrastructure in the whole Japan. For the buildings, it's a 1 kilometer by 1 kilometer mesh data, and you can see the spatial distribution of the material stock of buildings. And for the infrastructures, it's a 10 kilometer by 10 kilometer mesh data. And you can also see the development of the network of those infrastructures. And those 2 material stock flow database, we are trying to improve the accuracy or updating the latest version, or also expand the target of the infrastructures. For example, currently we are working for the database collection of the river embankments and sewage pipes material stocks. But 1 kilometer mesh or 10 kilometer mesh data is sometimes not sufficient to talk about the regional risk of the climate change. So we also have a very detailed high resolution data on material stock flow database in a city scale. This is an example, but in the specific cities, because it's really like takes time and energy to work for those detailed informations. So this is an example of Nagoya City database from 2006 to 2020. Unfortunately, 2014 is just like the data is being modified now, but I can show you quickly from the beginning from the past to the current material stock. So in 1960s, this is the center of Nagoya City. You can see the railway here, and this is the main station of Nagoya, the Nagoya station. And here you can see the blank. This is the area of Nagoya Castle. So in 1960s, we don't have many buildings, and the color shows the different types of structures. Green color shows the wooden buildings, and red color shows steel structures. So at the year of 1960s, we have many wooden and steel structures. Then after 10 years later, we have more and more buildings, and the color has been also changed gradually. You can see the transition of the urban environment from those databases. Yeah, just quickly go back to the past. So you could see many green color and red color in 1960s, but you may notice that the color is changing to more blue, and the height of the buildings are getting taller. So along with the economic development in this area, we have more and more reinforced concrete structures and more like skyscrapers or commercial buildings with a higher ground level is my height of the buildings. So sorry, I will quickly check the. And so how can we apply those databases for the further analysis? So I picked up 2 examples in our research project, how to use those databases for the analysis. Because the material stock flow database in high resolution is very foundational for every research in our group. So here, one example from here is a dynamic material stock flow analysis in the flat disk area in Nagoya City. So the left figure is shows the material stock of feedings in the 50 meters mesh. I just show the data of 2021, but we have a continuous temporal database from 1960 maybe. So you can see the transition of the Nagoya City here. Then by overlaying the information of future flood risk here, you will know how much of those material stock of buildings can be exposed to the risk of floodings. Especially in this area, about 50% of the area in Nagoya City are predicted to be affected by flooding in future. And we have many human activities in those areas. So because by using those information, we can expect the scale of disaster damage in future. And it's also useful for the policymakers to decide where to locate the new buildings or the structure height to avoid the risk of future flooding. And the other example here is a CO2 emission estimation by disaster damage on urban structures. This research aims to estimate the potential amount of disaster waste and its accompanied CO2 emissions based on hazard information. Here is an example of Kumamoto earthquakes occurred in 2016. So by overlaying the information of such as seismic intensity or the distribution of existing buildings, we will know how much disaster waste comes from that area. And also because we have many wooden houses in Japan, you will also know how much CO2 emission can be happened by those disasters, because the timber construction materials have a fixed carbons inside because of the carbon absorption and fixation function of the trees. So we are trying to make a model of how to estimate those carbon emissions derived from the disaster damage can be occurred by a climate change in future. So yes, these are just a part of our research project. So if you're interested in, you can go to the S18 project in our tab theme for 2 pages. But from now, I will move to my own research topic. That's the second highlighted one. Yeah, so let's move to my presentation now. So my presentation is about effects of altered building retention time and future material metabolism and carbon emissions. So there have been many individual initiatives against the climate change in Japan, and those are officially become an act, Climate Change Adaptation Act in Japan in 2018. And this act proposed that climate change issues should be approached both in a way to keep climate change under control, and in the other way to deal with the possible potential damages by climate change which can be occurred in future. So those mitigation measures and adaptation measures are kind of 2 ways of a same card. So we have to consider the good balance of those mitigation and adaptation in the long term to think about how to deal with, how to approach to climate change. So we really need to be careful how to think what kind of mitigation and adaptation should be adopted. Because as you can see from these figures, from the left, right, and bottom, inflow are becoming the stock and outflow are coming from a part of stocks. So those material stock and flow are interrelated in a very complex system in the short and long term. So we also need to consider how our decision, how our current decision affect to the future material stock and flow, and also its accompanied associated carbon emissions beyond generations. So perhaps when we think of the adaptations, maybe we need more materials to build a stronger buildings or more resilient society. But to make those urban structures, maybe we induces the carbon emissions or the other environmental burden in the background of those production and consumption or construction or this demolition activities. And we are still struggling for how to show how we can estimate those impacts with the specific numbers, but firstly, we need a framework to evaluate those systems in the long term. But that is not very easy because each of the material stock have a different characteristics. Like buildings and dams and ports are totally different in terms of lifespan, services, quality, and construction material contents. So it's not very easy. So we thought that maybe we can start with Japan's building data because we have relatively rich data in buildings. So we started from this trial in the case study of Japan's buildings. So this here is a model how to estimate the impact of material stock change to the future material metabolism and CO2 emissions. Firstly, we can somehow estimate the future demand for the buildings. And then we have a stock-driven material stock flow model. I don't explain the details today, but you use the stock-driven material flow model and estimate the future required inflow and outflow from those stocks. And because to produce those inflows or demolition of those outflow, we will have a CO2 emissions dependingly. So we have a coefficient for the CO2 emissions, then we can calculate how much materials are needed in futures and how much CO2 emission can be happened with the different scenarios. So the table shows the settings of the scenarios, and it's basically we have two scenarios that we continuously have the same lifespan of the buildings, that is no change for future, and the other option is have a more stronger buildings with an extended lifespan. So the material intensity also changes depending on this lifespan settings of the buildings. The reason why we have two laws here is it's something specific and unique in Japan, but we have too many vacant houses in society. So we have to think separately. The material stock definitely in use right now, and vacant houses which are already in vain left in society. Otherwise, we will have a very complex thought about the lifespan of the buildings. So that's why we have two laws here in the scenario settings. And just a quick and temporal result of the research. The purple line shows a scenario with BAU, so with the current lifespan of the buildings, and the green lines is a scenario with an extended lifespan of the buildings. And it seems that it makes sense that green line is higher in the beginning and lower at the end. That means to have a stronger buildings, we need the environmental burden at the first period, but because it can reduce the frequency of the turnover of the material, turnover of the buildings, it reduces the total amount of required new inflow and CO2 emission in the end. So the results simply saying that the amount of new material inflow and CO2 emissions can be reduced by about 30% by lifespan extension. But about these numbers, maybe we are not super sure right now, so I am still in the process of verification. So I will update you in the next ISIE conference or in the paper. And I think this is the last slide from me. And this model is, to be honest, still incompleted because the recycling of the materials are not closed inside the building sectors. Like we have a very high recycling ratio of aggregates in Japan, but most of the demolition waste from buildings are not goes back to the buildings. Mostly they are going to the road bed or the other infrastructures. So we have to connect the similar model of the other infrastructure next to this building's model, then make an arrow from demolition waste from buildings goes to the other section, the new construction of some infrastructures, blah, blah, infrastructures. But to extend the model to such interconnected infrastructure model, we have the big difficulty to know the future demand and supply of the recycled materials. Because in some private sectors, buildings or sewage pipes or electricity wires may have some relationship with the human activity. So we can maybe have assumption that it can relate it to the population change. But some public works are not following those theory. So we are still thinking how to estimate or predict the future demand for those public infrastructures. Maybe we can use some socioeconomic changes factors or the demographic factors. But because we have the turning point of the population around 2010 in Japan, so that was peaked at 2010. So it's really hard to predict from the past trend to the futures. So maybe it's a big discussion. So if you have good idea or suggestions, I really would like to talk with you. And yes, that's all from me. Thank you very much for listening. I will pass it to the next presenter. Thank you very much for listening. So I will invite next presenter, Daiki Sawa, please. So I will invite the next presenter, Rion Yamada, please.
Can you hear me and can you see my slide?
Yes, thank you.
Okay, so my name is Rion Yamada from Nagoya University, and this is the title of my presentation. Today, I would like to talk about the impacts of introducing compact city models utilizing building stocks on the urban thermal environment. Okay, so the population of many Japanese cities are declining due to the low birth rates. For that reason, the concept of compact city models has received a great deal of attention. And population decline also causes the problem of vacant houses. According to the Ministry of Internal Affairs and Communications, there are more than 8 million vacant houses, well, which accounts for 13.6% of all existing houses in the country. And as for the air temperature in urban area, there are two warming problems, global warming and urban heat island. And because these two warming problems have already worsened the thermal environment in urban area, it is crucial to estimate the temperature rises caused by these two warming problems. And the purpose of this research is to assess the impact of introducing compact city models while utilizing housing stocks on the urban thermal environment under the progress of global warming. In this research, firstly, we designed compact city models for Aichi Prefecture in Japan utilizing available housing stocks. And secondly, we made a future projections on the thermal environment in the designed compact city models. And we classified temporarily vacant rental houses, temporarily vacant houses for sale, and other vacant houses as available housing stocks or unavailable housing stocks. Well, available housing stocks are the houses that can be utilized without expense or major repairs. And on the other hand, unavailable building stocks are houses that can be utilized with expense or major repairs. And in order to estimate the number of available housing stocks, we utilize the equations that I showed in this and next slide. Equation 1 represents the way to get the number of available housing stocks per grid in the target period. And equation number 2 represents the way to get the total number of vacant houses in the target period. And equation number 3 represents the way to get the number of increases of the number of vacant houses. And equation 4 represents the way to get the number of unavailable housing stocks. By utilizing the equations that I showed previous slides, we can get the spatial distribution of available housing stocks in the 2030s and 2050s, as shown in the slide. And in this research, we classify the urban areas into two categories, the population-induced area and population withdrawal areas. Here, we assume the population in the population withdrawal areas were moved to the population-induced area evenly. In addition, we introduced two treatments of the population withdrawal areas. And one is the case with no change. The another is the case of changing into the grassland. As for the classification of urban areas, we classify them into the population-induced areas and population withdrawal areas based on the population. If the population in urban area was 2,000 or less, the area was classified as the population withdrawal areas. And if the population was more than 2,000, the area was classified as the population-induced areas. In addition, we divided the population-induced areas into 5 categories, G1 to G5, based on population. In this research, we conducted future projections of the urban thermal environment by using dynamical downscaling simulations based on the pseudo-global warming data proposed by Kimura and Kito. Roughly speaking, dynamical downscaling simulation technique is an interpolation of the result of global climate model known as GCM using regional climate models. In the case of combining the pseudo-global warming method, the linear coupling of the difference between future and past or present climatic element projected by a GCM and objective analysis data or reanalysis data is given to the initial and boundary condition for an RCM. In this research, we introduced GFDL CM3 as a GCM and weather research forecasting known as WRF, a double RF model, as an RCM. And these are the urban parameters for the urban canopy model in WRF simulation. By giving this urban parameter to the urban canopy model, we can properly reproduce the physical impacts of the compact city models designed in this research. As for the average height of buildings and anthropogenic heat release, they are calculated based on the population in each group. And as for the urban fraction, it was determined based on the population. A total 7 cases were conducted in this research. As for the target period and month, we selected August, the 2013, August, and the 2050s. For comparison, a past analysis of August 2010 was performed. As for the urban structure, we introduced the present urban structure and compact city models. And as for the treatment of population with rural area, we introduced 2 cases, the case with no change and case with replacement with grassland. From now, we are going to take a look at results. This figure shows the spatially averaged and monthly averaged diurnal variation of air temperature at a height of 2 meters among case 0, case 1 to 1, and case 2 to 1, comparing the average values over time, namely the monthly average temperature, the difference between case 1 to 1 and case 0, and that between case 2, 1 and case 0 are 1.772 Celsius degrees and 2.64 Celsius degrees, respectively. These temperature rises were caused by the progress of global warming. And this figure shows the spatially averaged and monthly averaged diurnal variation of air temperature differences at a height of 2 meters between case 1 to 1 and case 1 to 2, and that between case 2 to 1 and case 2 to 2. Regarding the average value over time, the difference between case 1 to 1 and case 1 to 2, and that between case 2 to 1 and case 2 to 2 are minus 0.01 and 0.00 respectively. Comparing with the temperature changes caused by global warming, these temperature differences are considerably small. And this figure shows the spatially averaged and monthly averaged diurnal variation of air temperature differences at a height of 2 meters between case 1 to 3 and case 1 to 2, and that between case 2 to 3 and case 2 to 2. This figure shows the impact of treatment of the population withdrawal areas. Regarding the average value over time, both differences between case 1 to 3 and case 1 to 2, and between case 2 to 3 and case 2 are minus 0.10 respectively. In complexity model, the treatment of population withdrawal areas is crucial to improve the urban thermal environment. And this is the conclusion of this study. In this research, complexity models actively utilizing available housing stocks were designed, and we made a future projections of the thermal environment in the design complexity models by using the dynamical downscaling simulation, and the impact of progress of global warming on the urban thermal environment was larger than that of the introduction of the design complexity models. And the temperature increases by introducing the complexity models designed in this research were considerably small, and in complexity planning, the treatment of population withdrawal areas is crucial to improve the urban thermal environment. And that is all for my presentation. Thank you for your attention.
Thank you very much. So next I will invite Yueyang Bai. Thank you.
Thanks.
Start
I
your
will share my screen now.
Yes.
Does it works well? Okay, thanks. Thanks so much. Good afternoon, everyone. I'm Yueyang from Nagoya University. It's a great honor for me to have the opportunity to speak at this meeting. Today, the subject of my presentation is mapping the high-resolution carbon emissions associated with Japanese building activities from a multi-scale perspective. I will start with a brief background introduction. As you probably all know, in Japan, both of national and local governments have submitted their carbon reduction targets in the commercial and residential sectors. But at the research perspective, previous studies have mostly been conducted in a single spatial scale or only within a single city with a specific geographic background. Then the regional emission characteristics at lower scales may be ignored. So now we wanted to explore that whether there are any differences in the spatial temporal variations of building carbon emissions at different spatial scales. For the estimation approaches, I wanted to show this table to summarize the application and the limitations of the four main approaches to calculate the life cycle carbon emissions of regional building activities. And based on this method, we can choose the appropriate quantitative method based on our research objectives. Combining the existing quantitative methods, now we have constructed a hybrid bottom-up methodology framework. Firstly, based on the 4DG's building stock database, along with the statistical data and investigation data, we estimated the life cycle carbon emissions for each building over the course of a year in Japan, and then aggregate these emissions based on the administrative boundaries to different spatial scales. Next, I will go through with these three main results in the presentations. Firstly, we aggregate the carbon emission results from the single building level to the municipality level and the prefecture level. And we can see that within each prefectures, different carbon emission distribution patterns were observed. Taking Tokyo, Aichi, and Fukuoka as examples, the building carbon emissions of municipalities within these prefectures were evenly distributed between the maximum and minimum values. But for other prefectures, especially some prefectures in the southern Japan, the emission levels of specific cities are quite higher than those of other cities. Then the more stringent building carbon emission management policies need to be implemented in these high emission cities to promote a more balanced overall emission level. And then in the same way, the carbon emission results were aggregated to the national level. And the national temporal trend is observed, is obtained from 2005 to 2020. Meanwhile, considering the unique socio-economic background of each municipalities, such kind of time trend may not necessarily apply to all municipalities. So in order to quickly identify the municipalities with different temporal variations in the huge data matrix of building carbon emissions, we conduct the empirical orthogonal function decomposition. From these results, it's important to note that unlike the national development trend, some cities, like several cities in Chiba Prefecture, which provided the bedroom service for economic centers, show an upward trend of the regional building carbon emissions due to the high population migration in the recent years. And these kind of cities have a large residential building stock, so improving the energy saving performance of housing, especially rental housing, is very important for this local government to achieving the emission reduction goals. Meanwhile, considering the spatial and temporal variations in building carbon emission distribution in above results, we further compared the regional carbon emission inequality at municipality level and the prefecture level using the coefficient of variation and the Gini coefficient, aiming to assess the emission imbalance across different regions. And then from these two figures, we can see that the regional building carbon emission inequality in Japan was gradually widening, especially at the prefecture level. Then in order to address the reason for the widening inequality of regional building carbon emissions, we further calculated the regional inequality of population and the per capita building carbon emission at the prefecture level. In terms of per capita building carbon emission, we can see that its inequality decreased sharply in 2011, possibly influenced by the energy structure transformation due to the Great Earthquake. And then its inequality showed a weak upward trend. But overall, the regional population inequality show a continuously increasing trend, which seems to be the main reason for the expansion of the regional building carbon emissions inequalities in Japan. The above are the three main findings in the presentations, but due to the time limitations, I will not repeat them. That's all for my presentations today, and thanks for your attention.
Thank you very much. So now for of the presentation I've already done. Thank you for all of the presenters, and thank you for the perfect time management. So now we have 5 minutes for the open discussions. Do you have any questions or comments to the presenters today? If you have, you can open your mic or raise your hand here. And could you turn on your video, the presenters? If possible. Yeah, thank you. Do you have any questions or comments? Or if you hesitate to talk aloud, you can also write the question to the chat. Should I ask the questions to the presenters or? Okay, some of them are already reading. Yes, so finally, here I put the QR code of our project and our laboratory, and here is my emails. So if you want to make a contact with all of the presenters today, you can send a message to me, email to me, or just access from the QR code to the project. And today's session will be uploaded to YouTube in the other days. So you can also check the details on the YouTube. Professor, you're here? Should we ask a question to the presenter or just close the session? How do you think? 4 minutes left. Okay.
Then let me ask a more general question rather than for the specific topic of today's presentation. That today I could learn many things from you all the presenters, and I'm wondering some of your presentation is related to more very specific area. So then we can study on the city level or more smaller area, and also more larger area or national level. So what can we do for different scales? I mean, when we study on more specific area, then it's a very special knowledge on that area. So how can we generalize them and in a more small area, meso area, or larger national scale? So Yamashita-san or Tanikawa-sensei, how can we manage those different scale studies?
Thank you for the question. I think we have like 2 teams in our research group who are working for a top-down approach and working as a bottom-up, like Yueyang's is very detailed, high-resolution data. So for example, her research is really useful for the local government to think of their policies, how to deal with the climate change and the coming risks of the disasters. But it also should be along with the whole picture of the country. So firstly, we have a target of the countries, so we can upload like maybe CO2 deduction by several % by 2050, but the local government don't know exactly how they can contribute to those numbers. So they can approach from the bottom-up approach based on those high-resolution research in the local specific area. And maybe finally, we will have the discussion from the 2 sides to have an integrated suggestion to the government or local government finally in the end. I think so. And if you, any of the presenters would like to answer this question as well, you can also open your mic. Thank you. thank you very much. And I have another questions from the floor. Very interesting work. I am wondering if the presented method can be applied to the other countries globally. Thank you. Thank you very much for the comments and the questions. Yeah, we are really happy to collaborate with the research institute in the other country, of course, because each of the country have a very specific trend or characteristics, and some country it works and some countries doesn't work. So we also look for the general way to contribute to the whole world. But because there is a data unavailability in some countries, it's really hard to access to those research. So if you are interested in to join the similar research in your country, maybe it's really nice opportunity to work together with our group. Thank you very much. So it's time to close. And please give the presenters a big applause or good buttons. Then I will end this session. Thank you very much for coming today and see you soon.